Okay, so here we go. So what is this, 2012? Number 8, multiple choice. So the maximum mass that can be hung from it is 10 kilograms. That means our maximum tension force, our maximum centripetal force, is the weight of 10 kilograms, which is 100 newtons, right? Just 10 times 10, using 10 for our acceleration of gravity. All right, and then it wants to know what's the maximum speed that it can attain if you spin it around at the end of a rope that's 2 meters long. Well, centripetal force is mass times velocity squared over radius. And just solve for v. And so you end up getting 20 meters a second there. Cool? I don't know who asked about these ones, so. Let's see, number 10. It says a particle of mass m starts from rest at a position x equals 0 at time 0. It moves along the positive axis under the influence of a single force, Fx equals bt. So you've got this horizontal force, and it's equal to bt. It says the velocity v of the particle is given by, and you got to find an equation. So, thoughts, you guys? How do we? Our goal is we want to come up with an expression for the velocity at time t. So, sure, yeah, you can start, Anthony.
What I was thinking is just like find the units that it needs to be.
Oh.
So you know that has to be newtons.
This is clever. So, okay. So this has to be newtons, which means...
Kilogram meters per second. V would be kilogram meters per second.
Cool. So you're saying that 1 newton is 1 kilogram meter per second squared. So if we're multiplying b by t, then b must be in units of kilogram meters per second. Right? Oh, it's seconds cubed, yeah. Thank you, my bad. All right, so that's the units on B, and so then we need to figure out what you have to do to B to end up with meters per second. And so process of elimination, choice B is the only right answer. Is that kind of what you did? Yeah? Okay, that's cool. I wouldn't have thought of doing it that way. That does work.
The only thing is you don't get the 2 with that.
Yeah.
That was what I was about to say, is then how do you figure out if it's B or C?
Yeah.
Gotcha. Okay, so that's problematic. All right, so let's see if we can come up with another approach then. Thoughts? Jacob, you got an idea?
F equals ma, and solve for a, and integrate a to b.
Yeah, I think that's the way we got to go about this. We need to find a path that gets us from force to velocity, right? Force depends on acceleration, and velocity is the derivative of the acceleration. So I'm looking at this. Mass times acceleration equals bt. Acceleration equals dt over m. That means dv dt is bt over m. So integrate both sides with respect to t. Well, multiply by t and then integrate. That's crappy notation. What I just wrote there. dv equals the integral of bt over m dt. Yeah, and so when you integrate, you get bt squared over 2m. Cool? Too fast? All right. So that was number 8. Let's see, number 12. What are we trying to find? We're trying to find the time. Okay, so here we go. Number 12. An electric motor provides 0.5 watts. What is 0.5 watts a measure of, you guys? Power. Not work. Power, right? And if you forget, remember that's the same as joules per second, right? Okay? It says how much time will it take the motor to lift a 0.1 kilogram mass at a constant speed from the floor to a shelf 2 meters above the floor. So our mass is 0.1 kilograms. We're trying to lift it up to a height of 2 meters. So what should I do with this garbage, you guys? Yeah, find the GPE, right? So if you do MGH, you end up getting 2 joules. So we need to give a thing 2 joules of energy at a rate of 0.5 joules per second. So I thought of it this way. I said power is the change in energy per unit time, right? So 0.5 equals 2 over t, and then solve for t, and you get 4 seconds. Cool? You could also do power as force times velocity, and then solve for the time for the velocity to work, but this was easier, I thought. Cool? Sarah, you okay back there? You're craning your neck. You good? Yeah. Everybody set? Yep. Alrighty. What do we got next? Let's see. 13. It says a block slides from. Oh yeah, this is the one where you've got the drawing. Ooh, I'm very happy with that little drawing. All right, so here's our block. No friction. Friction. Shh. This guy is 5 meters tall. We want to figure out what distance it's going to slide before stopping. Thoughts? GPE and KE? And then net force at the bottom. Okay, so there's a couple ways of doing this. I agree you could do GP and KE. So that means that, let's see, mg times 5 is equal to 1/2 mv squared, right? And solve for the velocity at the bottom. Everybody agree? Okay, and so that gives you the velocity at the bottom. Is this the way you did it, Evan? Okay. Does anybody know what the velocity is? I did it a different way. 10 meters a second? Do I agree with that? Yes, I do agree with that. It does give you 10 meters a second. Okay, cool. So then once it's stopping, so we're going to do this. 2a delta x equals vf squared minus vi squared, right? But we need to know our acceleration. So how can I find that acceleration? Force of friction, right? So make your little free body diagram. Your force of friction is going to end up being 0.2 mg, right? Which means your acceleration is 0.2 g, which is what, -2, right? Cool? All right, so that works. Anybody do it differently? You can do it in one step. Because look, the block is going to begin with GPE, right? Okay? Isn't friction a non-conservative force? Right? So this should equal the work that friction does times the distance d. Right? Because your energy has to go from whatever down to 0. Follow? So you get mg times 5 equals coefficient of friction times mg times d. Your mg's cancel. So you get 5 equals 0.2 d, and you're done. Cool? All right, what's next? 17. Ooh, that was a popular one. Or unpopular, I guess, depending on your perspective. 17. Spring constant. Well, based on the graph, just by looking at the graph, I can see that the period of oscillation is 1 second, right? So do you guys agree that my angular frequency should be 2 pi over t, which is just 2 pi? So, and then we learned that the spring constant is just m omega squared, right? And so we know the mass, we know our omega, and you just plug in your numbers. It gives you 16 newtons per meter. I don't mean this in an asshole way, but what was hard about that? Like, why did we get messed up on that problem? A lot of people asked about this one. So, question about that, or?
No, I was just going to
You sure?
Yeah, I just needed some tips before.
Okay, gotcha. How did you do it?
It's like basically the same way, except it's just like the one with periods.
Oh, gotcha. Where you do t equals 2 pi root m over k. Gotcha. Yeah, you know your period, you know your m, solve for k. Gotcha. So where did we get messed up on this, you guys? Okay. Just couldn't remember it. Okay. Here you go. All right, so everybody's good on 17 now? Yeah, Molly? No. Don't, wait, let's see. Oh, I see what you're saying. So you're, ooh, this is slick. I like that. So what you're saying is, so you used your force of gravity. So that's like 4 newtons, right? And then what did you do?
The setting through the K times the distance traveled.
Gotcha. Did that? I don't think that works because, so it says a 0.4 kilogram object is attached to the lower end of a spring. So that's this. It's then pulled down 0.35 meters. So this force does not correspond to the 0.35 meters, which is why, so that doesn't give you the right answer, and that's why. Does that make sense? Everybody, does that make sense? Gotcha. Yeah. Okay. Let's see what do we got. So that was 17, 19, and 21 are next on the list. Number 19. It says the uniform thin rod shown above has a mass m and length L. And you're given this rod. You're told that it has a length L. This point P is a quarter of the way from the end. It tells you that the rotational inertia about its center is 1/12 ml squared. And it wants to know what the rotational inertia about point P is. So what type of problem is this, you guys? Parallel axis theorem, right? Because we know an expression for the rotational inertia about the center of mass, and we're moving it over, right? So the rotational inertia about point P is equal to the rotational inertia about the center of mass plus, it's mh squared, right? What does h represent in words?
The distance from the center.
The distance you've moved your pivot point from the center of mass, right? And for us, that's going to be L over 4, right? Don't forget to square it. So I'm looking at 1/12 ml squared plus 1/16 ml squared. So then you just got to add a 12th and a 16th, which gives you, what, 7/48? Cool, you guys? All right, so that's 19. 21. Which of the following is a differential equation that correctly describes Newton's second law for a simple harmonic oscillator of mass m and restoring constant k? So Newton's second law is this. Simple harmonic motion means that the force is proportional to the displacement. So then we just need to write an expression for that. Well, let's see. It looks like they're talking about derivatives here, right? So, also there's a mistake here. What's wrong? I forgot a negative sign, right? Right? Because your acceleration is in the opposite direction as your position.
Yep.
Cool. So here are, I think, the two correct answers. You should have m dv dt equals negative kx. Is that one of the choices? Nope, that is not one of the choices. So let's take another derivative. Taking one more derivative gives us, I always forget where the 2's go. Right? This is just saying the second derivative of position, right? Good, you guys, or no? Any problems? All right, what do we got next? Oops, we've got me not knowing how to use my smartboard. Wow. So pretty much the rest, except it looks like we can skip 25 and 29. Wow. All right, second half of this looks like it was tough. Shoot, what did I just say?
25.
Right, but where do I need to start? Oh. Okay, here we go. Let's muscle through this. If I'm going too quick or losing you, stop me, all right? So 22 through 24 are all about an orbit. So you're given this drawing. The sun is labeled, and then point 2 is labeled, and point 1 is labeled. The text tells us that if this distance is d, then this distance is 10d. Right? It tells you it's 10 times as far away at position 1. Good? What's going on? Are we good? Like as opposed to like 90?
No, is it like chicken tenders?
Yeah. Say chicken tendies instead of vendor tendies.
I don't know that I've ever been this confused in this class before. Is that a thing? Tendies? Chicken tendies?
Yeah.
From what?
Just like that's like what people call chicken, like chicken nuggets, chicken tenders, like chicken tendies.
All right.
Really stupid.
Huh. All right. Well, there you go. Okay. So let's talk about this. So there are a couple of questions here that deal with kinetic energy and velocity, right? So at what point in the orbit should the velocity be the biggest? When you're close to the sun or far from the sun? Close to the sun, right? Okay. So question A says at position 2, the comet's kinetic energy is, well, that kinetic energy is going to depend on the speed, right? And since it's going fastest at point 2, because that's where it's closest, that should be the maximum kinetic energy. So that's 22, it should be C, right? All right. 23, it wants to know something about the ratio of the speeds. All right. So do you guys remember, how do you relate the radius to the velocity? Yeah, it's conservation of angular momentum. The mass of the comet times the radius of its orbit times the velocity is a constant value. So at point 1, that's got to be the same as at point 2. The m's cancel. Cool? So if you've got 10 times the radius at point 1, that means 1/10 the velocity at point 1. Follow? Mm-hmm. All right. And then 24 is asking about the forces. Name the force we're talking about here, you guys. Gravity, right? So force of gravity is G times the mass of the sun times the mass of the comet over some distance squared. 10 times the distance means 1/100th of the force, right? Because of the squared?
Yes.
Inverse square? Cool? All right, so that's 23 through 24. Is anybody unhappy about those explanations? All right, 25. You've got a block of mass m. You're pulling it this way with a force F at an angle phi to the horizontal. You're pulling it at a constant velocity. It says, which of the following is an expression for the frictional force? So So the first thing I thought was, it's moving at a constant velocity. So, since it's moving at a constant velocity, doesn't that mean that the horizontal component needs to equal friction? Right? So I really thought the answer was going to be this. Right? Because if it's going at a constant velocity, then the friction has to equal the horizontal component. But that wasn't one of the choices. All right? Which means the fact that it's moving at a constant velocity is extra information you don't need to solve the problem. All right? So I think the only way you can do this is to go force of friction is coefficient of friction times normal force. Good? So what's your normal force going to be? Well, it's going to be my force of gravity minus whatever's taken away by this vertical component, right? Sorry, I turned my phi into a theta, but you get the idea. Cool? I guess the fact that it's moving tells us it's kinetic friction, right? Cool? So that's 25. 26. What do we got? 4 kilograms and 4 kilograms. And then your rope does this. And it wants the tension in the rope. Remember, you guys, you don't add. Gravity's pulling this guy down with a force of 40 newtons. So what does the tension have to be? 40 newtons, and you're done. Okay? You don't think of it like 40 plus 40 is 80. It doesn't work that way.
Or I could do it from acceleration to 0.
Right. Everybody good? All right. So that was 26. 27. A person throws. All right. So 27. A person throws a ball of mass 0.2 kilograms. It starts at rest. It accelerates horizontally and uniformly through a distance of 0.90 meters and leaves the person's hand with a final velocity of 30 meters a second. We're trying to find the force from the person's hand. Good? So, thoughts, you guys? Yeah, we can use this guy. To find our acceleration, and then the force should just be mass times that acceleration, and you're done. Cool? All right. 28. I have a large boulder in my eye. Ow. All right, 28. You got to watch your signs on this one. You've got a railroad car. It's 1,500 kilograms going to the right at 4 meters a second. And it's going to collide with another car that's 3,000 kilograms going the other way at 3 meters a second. So you got to make this guy negative. All right, and they stick together, right? So it's a perfectly inelastic collision. So you should have 1,500 times 4 plus 3,000 times negative 3 equals 4,500 VF. Solve for your final velocity. You get 2/3. Cool? 29. It's a meter stick. That's important because it's 1 meter long. That's how they make meter sticks.
How do you come to that conclusion that it's a meter long? It's not that it's a meter stick.
So let's see. The fulcrum is at the 0.4 meter mark. So you've got half a kilogram from, a 1 kilogram mass is hung at the 0 mark. So 1 kilogram, so that's going to be 10 newtons, right? And then you've got a half a kilogram on the other side. So that's going to be 5 newtons. And you need to find the net torque. So that's 0.4. That's 0.6. So my net torque looks like it's going to be the torque from the 10 newtons plus the torque from the 5 newtons, and add them up. But I forgot something important. One of those torques has to be negative because they're working against each other, right? So make one of them negative, add it up, and you get 1 Newton meter. Cool? All right. Number 30. Object undergoes simple harmonic motion, blah, 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 blah. You want to find a graph that relates the acceleration to the position. Well, look. F equals negative kx, right? That's the definition of simple harmonic motion. Oh, that means acceleration is negative k over m times x. Right? So here's my y-axis, here's my x-axis, this is my slope, it's negative. Okay? So it's got to be a, because that's the only one that is linear with a negative slope. Follow? Too fast? Are we good? 31! This is the one that I thought was neat. It says a ball is dropped. So you've got one ball that's being dropped from a tower and another one's fired up with some initial velocity. You want to find the time at which they pass. So what you need to do is write an expression for the position of them. So the position of ball 1 as a function of time should be 1/2 g t squared. Make it negative because the acceleration of gravity is down. Your initial velocity is 0, but it begins at a position of h. Right? Does that make sense, you guys? All right. Similarly, nailed it. Object 2 begins at a position of 0, but it's got initial velocity. So now what do? Set them equal to each other, right? And this was what I thought was neat. This part all cancels out, right?
Just add it.
Right? So you get VOT equals H. Divide both sides by T and you get H over VO. That was gross. All right, everybody good? Okay. The other way to think about it is if you think of it from the frame of reference of either the objects, they both have the same acceleration, right? So relative to each other, they're not accelerating. They begin a distance of h apart, and one of them is moving at a velocity of VO. So, let's see, 32. This is a good calculus-y one. It says, suppose the potential energy of a particle is given by this. Where K and A are positive constants. Stable equilibrium points about which the particle oscillates are located at blah, 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 blah. What do we mean when we talk about a stable equilibrium point, you guys? It's an equilibrium, which means what? Net force is 0, right? So equilibrium means net force is 0. Okay, and Evan, I saw you doing this. Do you remember what the deal was with that?
If you give it potential energy, it will just go back to where it was.
Good, yeah. So if you plot potential energy, stable equilibrium point, unstable equilibrium point, neutral equilibrium point. Does that vaguely ring a bell? So we want to find a point where our net force is 0. So let's start there. So how do I get from this graph, oops, try again. How do I get from this function to net force? Derivative, right? With respect to x. Okay? So f is negative du dx, right? So take the derivative and you get, let's see, what? Negative kx plus a, right? Cool? And we're going to set that equal to 0. So you get A equals kx. X is A over k, right? So then I would say you need to make sure that that's a minimum. But if it's not, then there's no stable equilibrium points, which wasn't a choice. Right? So the only choice then is B. Make sense? All right. Yeah, Adam.
I did it the way where you took the integral. So like you have u is equal to
U is, that boils down to the same thing. Yeah, that's fine.
but it also brought a 0.
U is equal to the integral of f dx. Like that. Oh, I see what you're saying. So where did you go from here?
No, I don't actually know. I can't think of that. Like, I wrote like some stuff down that's not making sense to me right now. So I'll just
Yeah, so I didn't graph it. I guess that's a parabola, so it can only have one local minimum, right? So at 0, the potential energy is 0, but the slope is not 0. So 33, you got to be really careful with your signs. I know the bell's about to ring. I got this one wrong, you guys. All right, when I did this, I got this one wrong. Because you're trying to find the change in momentum, right? So change in momentum is mass times VF minus VI, right? So I just immediately put B. All right? But that assumes these are vectors and you're given magnitudes. So VF and VI are both positive. So you have to add them to get the change, right? So that was why that one was C. All right? All right, finally, I know the bell's about to ring. All right, we'll talk more tomorrow. We'll do the FRQs tomorrow, you guys. If you didn't finish them, that's your homework tonight.
Like the other day.